Alrighty, ladies and gentlemen, time for our DC circuits concept map. So what we got here so far is we have part of the concept map already drawn out for us, just so things can run a little bit more smoothly, and then from the rest I'll be writing it as well. So what I want to note over here first is this part right here pertaining to circuits. So three things have to always be active for a circuit to be working. You need to have a closed loop, so your electricity needs to go in a full circle. There needs to be a power supply at some point in it, and you need something to cause a resistance to happen. If at any point any of those aren't happening, then you run into some problems, either be a short circuit or non-working circuit or just an open circuit. Below, you'll find a couple of things are bits and pieces when you're drawing circuits or reading circuits. What you need to be able to see is lamps or bulbs are often denoted by a circle with an X through it, or sometimes with just a little bit of a loop. So if I were to draw this a little bit better, let's see if I can. Here we go. Sometimes drawn with just a loop on the inside. Resistors are just a little EKG heartbeat sensor looking thing. Batteries are a series of long and short lines where the short line is denoted as positive and then the long line is denoted as negative. You have voltmeters and ammeters. Voltmeters measure voltage, ammeters measure amperage, and you have a switch and a rheostat. A little bit, maybe I won't get into it later, but we can get to it right now, is voltmeters. Those have a resistance of infinity, and so they go across the circuit, all right, not in it, and ammeters go in your circuit, all right, so inside circuit. Okay, so looking over here on the right side now, looking at Ohm's law, how it breaks down. V equals IR is what we talked about in class, but it looks like on your reference sheet as V equals delta V over R. Now when you unpack delta V here a little bit, delta V can be potential difference, electromotive force, voltage, or it can even be written as joules per coulomb and just giving the units. All of these for this class essentially mean the same thing. Current, however, is the part where people think voltage is the part that kills you. Current is the part that actually kills you, because that's denoted as how quickly that charge is traveling through your circuit. Current is measured in amps, and on your reference sheet you'll notice that current can also be calculated by your change in charge over your change in time. So basically, how fast are those electrons flowing through the circuit. Last thing would be resistance. Resistance is measured in ohms. And so ohms is denoted by this little lowercase Greek letter. I'm going to write that just a little bit more clearly. There we go. Lowercase Greek letter, or just written out as ohms. Every once in a while they like to throw a little trick at you and give you kilo ohms rather than regular ohms. So be careful on if there's any prefixes in front of your units. Next thing I'm going to do is unpack couple things. Is what does the difference between resistance and resistivity. So I'm going to go over here to resistance, and so we're looking at resistivity. Resistivity. And that is denoted by R equals P L over A. R being resistance, P being, or this rho here being resistivity, L being length, A being area. If we unpack this a little bit, we already know resistance is in ohms, but what about this Greek letter of rho? Well, that's resistivity, and this is an intrinsic property. Means it does not change based off of how much you got. Oh, and let me erase that a little bit. Intrinsic, not intrinsic. There we go. Intrinsic property. All right, means it does not change based on how much you have. It does change based off of temperature or a couple other outside variables, but as far as this class goes, we're going to call resistivity as a constant. Now, some things like copper have a higher resistivity, or sorry, a lower resistivity than, let's say, plastic or rubber or things like that. And so, even though this resistivity is a number, it's often going to be a very small number. Like the resistivity for copper, I believe, is like times 10 to the negative 8th. It is denoted in units of ohm meters. So ohm meters. All right, what do we got next? We have length. So this is the length of your object. So this is denoted in meters. So if I have two objects here, so let's say two cylindrical objects. All right, and let's just go ahead and color that in real quick. If I've got two cylindrical objects, one is longer than the other. It's a little bit harder to do on this than it is with a marker. Let me go ahead and erase those real quick, and I'm just going to draw some shapes. All right. Oh, there we go. So if I have two objects with the same thickness but different lengths, how does that affect the resistance? So let me try this again. So if I have a wire here versus a shorter wire, so the longer your length, the more your resistance. And so this is going to have a higher resistance, and this would have a lower resistance because as the electrons flow through this piece of wire, they have a longer distance to go. And since this has a shorter distance to go, its resistance is going to be lower. All right. What about cross-sectional area, and how does that play a role in when you're looking at an object? So say if I have, so cross-sectional area is going to be meters squared. Let's say I have a larger tube. I'm going to try drawing some circles again. There we go. Versus a smaller tube. And then I were to take these tubes and I were to cut right down the middle, what would be my cross-sectional areas? Well, this one would be a larger circle, and this one would be a smaller circle. How would that affect my resistance? Well, if you have a larger cross-sectional area, a larger, I would say, path for those electrons to flow, your resistance is going to go down. If you have a smaller cross-sectional area, think of those electrons being jammed into one location, your resistance is going to go up. Now, this is something I really wanted you to unpack with that Play-Doh lab, playing with length and cross-sectional area and allowing you to determine resistivity. There is a wonderful FRQ practicing this skill. If you haven't done that, go ahead and try that before you take the test. Alrighty, what about some other things we've learned? We've learned a little bit about power. And so what does power look like exactly? So power, we've seen before as the change in energy over time, which is also denoted as work over time. Now, when we did power, this was in units of watts, and we're going to revisit that here in a second. When you're looking at the electrical power, you're still going to use watts, but it's going to be current times your potential difference or your voltage. Using V equals IR, we can rewrite or derive a couple different equations of this power formula. So power being watts still, we can say power could be I squared R, or we could use power being V squared over R. And how did I get to both of these? Well, depending on how I wanted to use this equation right here, we could say voltage equals IR and allow me to plug that right in there. Or I can also say that current equals voltage over resistance, and I can plug this in for I, and that would get you to either one of these derivatives right here. So if you're looking for power, you can find it one of three ways. You can find it using the formula given on your reference sheet. You can find it using if you do not know voltage or if you do not know current. In either case, power, when you're looking at an object moving, is going to be comparable to the power we've done before. And so what we got here is, if we look at power being work over time, if a motor is in place, we could look at its work being usually a change in gravitational potential energy over time. And so then from there we can set this equal to current times your potential difference, or voltage, or whatever you're looking for. But this, all we're saying is power, mechanical power and circuitry power have a role to play with each other. Depending on how you need it, you can change those variables around. But those two definitely interact. All right, one last thing before we're heading on our merry way, and that would be looking at series, parallel, and combination circuits. So we have, let's do series circuits first. Series circuits. What's given on your reference sheet is something that looks a little bit akin to this. That it says resistors in series is equal to the summation of those resistors. That's it. You have to have the overall science know-how to understand what this sigma means, and that just means summation. So if you're having a hard time doing that, I would just recommend you remember these things. All right, this is not given on your reference sheet, but nice to have in your back pocket. That resistor in series is an additive rule. So R1 plus R2 plus R3. Oop. What is not given to you is how does voltage and current play a role in here? Well, current is going to be constant. I1 equals I2, so on and so forth. And because of that, voltage is additive. Now, if you watched your Khan Academy videos or paid attention to the labs, you would notice that we talked about Kirchhoff's loop rule here. All right, Kirchhoff's loop rule says that the total voltages in a circuit, if you add them up, should be equal to 0. So whatever the battery is putting out and all the pieces in that circuit are using up, those should all add up to equal 0. And this follows the law of conservation of charge. So law of conservation of charge. Alrighty. What about parallel? How does parallel play a role in here? Before I forget, I'm actually going to draw what series looks like. I meant to do that beforehand. So series is where one resistor or bulb or whatever is using your circuit feeds into another. In parallel, what do we have? Parallel, and on your reference sheet says 1 over resistors in parallel equals the summation of the inverse additive of your resistors. Now, what I'd recommend for you to remember when it comes to this stuff is these formulas. I would remember the inverse additive, so resistors in parallel equals 1 over R1 plus 1 over R2, so on and so forth. This means your current is no longer constant, but your current is now additive. So I1 plus I2, so on and so forth. Your voltages, however, are constant. And so voltage 1 equals voltage 2, so on and so forth. If you pay attention, or pay attention to Khan videos or the lab, you will notice that Kirchhoff's junction rule plays a role in here. So Kirchhoff's junction rule. This means whatever is breaking off your currents, whatever branches they fall into, when they come back together, that current is going to come back together and be additive. And this follows the law of conservation of energy. Law of conservation of energy. So notice that Kirchhoff's junction rule and Kirchhoff's loop rule follow two different laws that we've talked about. And so you can kind of tuck those in your back pocket. Usually they pop up on that FRQ as just nice little one points to add on your FRQ. What does parallel look like? That's where two currents come off and then come back together. So Kirchhoff's loop rule means that when the currents branch off and they come back together, all right, that no current is lost there. Okay. Alrighty, ladies and gentlemen, I think that's going to be it as far as this video goes. Let me know what questions you have. Feel free to shoot me an email or message me through social media in some other way, shape, or form you need. This whole unit itself isn't necessarily too difficult, but is a nice little breather from rotational motion. Alrighty, guys, good luck. Let me know what you need, and I'll catch you later.